All right, thanks everyone for coming, and thanks for that introduction, Yifeng. Like was just mentioned, I run the Neuromotics Lab here at the University of Vermont, and we focus on methods for deep neural networks and machine learning, especially trying to make these artificial intelligence systems more like natural intelligence and more biologically adaptable and robust and scalable, and take what we've built drawing inspiration from biology and try and transfer it into the real practical use cases that have been emerging in science and clinical work and engineering recently. So I try and work kind of all across the spectrum from applied to really theoretical work. As Yifeng mentioned, this is part of the capacity building EBSCOR project, looking at how AI in advanced manufacturing will look like the next decade or so, in collaboration with some really awesome folks at in Maine and in New Hampshire, as well as throughout Vermont. So there's been amazing accomplishments in advanced manufacturing the last few decades, and Industry 2.0 looking at manufacturing lines, Industry 3.0 introducing robotics and automation. When we try and look forward into Industry 4.0 and try and think about what that looks like in terms of AI and advanced manufacturing, as we get more autonomy, as we get more connectedness, more IoT at the edge, I think of customizable, adaptive, autonomous systems. So this manufacturing plant, which is kind of the stereotypical factory floor I think of, has amazing precision, amazing reproducibility, incredible strength, but it lacks the robustness that natural biological systems have. If you were to pass in a different model of car, or even have the car, half an inch off on the chassis or the conveyor belt running through here, it would catastrophically fail at the task that each of these robots is assigned. And yet we have such great robustness in biological systems that would allow for more autonomy, more customizability, more adaptation in Industry 4.0. So there's a bunch of subfields within this grant that I think our work in AI and machine learning can help inform. I'm going to talk about a couple today. One, design automation. That the tools we have in advanced manufacturing, especially additive manufacturing and 3D printing, are actually far, far beyond our ability on the AI and machine learning side of things. This is an area, not actually my focus for this grant, but an area where we've worked a lot in the past in my group. And while we have printing capabilities at nanometer or millimeter precision with multiple materials, where complexity actually comes for free, that it's sometimes faster and easier and cheaper to print these really delicate, complex structures rather than solid blocks of material. But we don't have the design tools to help support these manufacturing processes, and really we're limited by our creativeness and human intuition and ingenuity here. And I think there's a real opportunity for generative design automation tools to play a big role in what 3D printing looks like the next handful of years. Talking about autonomous robots, when we think about machines that aren't just in the same place and can do their jobs because factory lines are so meticulously controlled, sterilized, repetitive environments, and think about robots out in the wild, moving around, doing many different tasks, dealing with one-off parts and environments and challenges. This becomes a much trickier prospect for them to be able to deal with something the very first time. This one-shot learning is an example of a well-trained robot that's seeing things it's never seen before. And even though this is a relatively simple pick and place task, is really challenging for this robot to control. And the ways that we typically get around this research was at Google Brain, is to have lots and lots of robots trying to do these tasks again and again. And to essentially make it into a big data problem of trying to figure out many, many different ways to solve many different problems. This particularly uses federated learning, which is a way of kind of sharing information across many, many robots. But this isn't really a scalable approach, and I think isn't a very biologically relevant way that that we could be solving this problem. Our labs worked with mobile robots. The lab I set up as a postdoc here was, again, just kind of looking at pick and place in relatively controlled environments, but was still really challenging. So we're in a really interesting place, I think, in machine learning, where things that seemed crazy and impossible 5 years ago are now well within the realm of what deep learning can do, or at least make significant progress towards. And yet there's still these really fundamental challenges of creative design, of adaptability, robustness, scalability, where I think that we can make really interesting contributions to foundational work in theoretical machine learning, and yet still play a real important role in the applied industrial parts of this NSF project. I feel really lucky to have found this group, since I did my PhD in an engineering lab that focused on robotics and 3D printing. And yet the part of that I spent most of my time on pursuing a degree in computational biology was the bio-inspired part of AI and machine learning here, looking at how animals behave, and especially how they adapt and come about through evolutionary and developmental processes. And it spun this into a great deal of work on learning as well. And a lot of what I'll talk about today is based on deep learning, kind of end-to-end learning across these big data sets, trying to pull humans out of the loop as much as possible and make automated autonomous systems. So I'll start the first half talking about generative design. There's folks on this call who've worked on this problem extensively, and I'd hope to foster some collaborations on this front as part of the EBSCOR capacity building. So let's start with a really simple project optimizing a single beam. So we have this beam fixed on one side at the four corners, and then we're going to apply a force at the other end, trying to minimize deflection while also minimizing mass. These two opposing constraints make it so that it's not entirely clear what the best solution is, but we can find heuristics that give us a pretty good job at approximating this. Some of these heuristics are really nicely biologically inspired. So this one that you just saw was based on the ways that trees respond to stress and grow based on environmental stimuli. So we show this process in slightly more detail. We have a beam here, or at least the space where one could exist, where we have cells growing and growing within it, and dying off as they undergo less stress and are less critical for the function of this structure. We can examine our found optimized structures and actually create many different variations of this just by playing with the hyperparameters of our heuristic. It was probably 10 years ago I built this tool, but also put in constraints to let us look at other similar types of problems. So here we have a beam fixed on two sides with a lateral force that ends up optimizing a structure that looks something like this, again, trying to minimize deflection and weight of this part. We can do all sorts of things like put a rotational force on the end and evolve structures that are optimized to try and minimize twisting. I think that the structures evolved here are really interesting. But the macro structure really just begins to scratch the surface, and there's so many directions we can go. One of them I think is really interesting. It's part of what we talked about in the grant is co-optimizing the macro structure with also the materials at the microstructure here, taking advantage of the extreme precision that we have in a lot of additive manufacturing processes. And this sort of multi-scale optimization is a place where my lab specializes. I think deflection and mass and stress are good places to start because they're really intuitive, but they're places where I think engineers do a pretty good job at building brackets and bridges. Places where solutions are maybe less intuitive might be things like vibration, resonance. These are really important material properties, and yet are highly nonlinear and often take place kind of within material structures that we can't really see. But the idea of absorbing energy for collection or dampening is a really important part of a lot of engineered systems. So we'll take that same beam, fix it at one end, add force to the other, but instead of looking at deflection, we'll look at what resonant frequencies this structure has. And we'll do that by placing some stiff and softer 3D printed materials within this beam, and try and do it in a clever way such that we have it resonate at certain frequencies. At least to me, I'm a terrible engineer, but at least to me and my collaborators, it seemed like a pretty hard problem to just intuitively design solutions for. But at least given the FEM models that we had, simulating these and finding out how good a proposed solution was is much more straightforward. And this kind of iterative guess and check process is actually coming back to our biological roots, very similar to how we see creatures and structures evolved in nature. So we're going to try and simulate that evolutionary process here, starting with some genetic encoding of our structure, and then building out, a beam, a robot, an agent, an animal, a human, and having that potential solution run through tasks. In this case, trying to match a given resonant frequency. The ones that do poorly, unfortunately, die off, but the ones that do well mate and reproduce and start this virtuous cycle over again. So we have this evolutionary process. Really, the next big question is, what's the DNA within this setup? We use a special type of artificial neural network called a compositional pattern producing network, which takes in the location of a voxel or a cell within this space. And by inputting the coordinates and applying them to every location within this frame, we can start to make really consistent geometric patterns. So for example, the X input gives us some horizontal gradient. One of the other special things about these networks is that they have non-sigmoidal activation functions, unlike most neural networks we use in deep learning. And so we can add, for example, a Gaussian function to give us symmetry along this x-axis, or put a sine function on our y-input to give us vertical repetition. And pretty quickly, we're getting complex patterns with these really sparse encodings inside of this neural network. Another thing I love about these is if you squint hard enough and wave your hands enough, this looks a lot like what's happening in biology, the composition of functions matching up with the composition of morphogens on top of each other in early embryogenesis. Again, kind of pulling a bio-inspired flavor. Thinking of this evolutionarily, this allows us to make big jumps within kind of our pixel voxel encoding space, but doing so in a much more condensed, sparse encoding or representation, which is to say, just by making a single change to the network that encodes this image, all of the images that you see are one mutation, one change away from the one at the top left. And their pixels are each very different, but they maintain a bunch of high-level features and abstract structure that lets us do things like evolutionary search and mutation in a way that's much more successful than doing so directly on our high-dimensional encoding space. What really drew me into this approach is that if we hook this up to a system where the survival and reproduction mechanism is based off of drawing people's attention, we get things that really are quite eye-catching and look and feel very complex and biological. So rather than make interesting artwork, which is a whole nother talk in itself, we're going to take this structure and fill out the 3D printed materials within our beam. We tried to match a profile of the top 10 resonant frequencies of these structures. After the first couple, it really stops making sense. But at least according to our finite element simulations, we're able to match them nearly perfectly with these evolved structures. And what's, I think, most interesting to me is just looking at the patterns and consistency of different iterations, different trials, using these same profiles that we're finding structures that, at least to me, tend to look really similar, as if they're finding solutions to a specific type of problem, represented by these 4 different types of resonant frequency profiles. And of course, we have a big, awesome 3D printer across the room, so we'll take these and actually print these out and look at the materials in real space and time. Where can we go from here? There's a bunch of interesting directions, and I wish I had more time to talk about all this work, but the next thing I want to talk about, and I think the place to go, tying in the additive manufacturing into some of the robotics aspects of the work that I'm going to talk about next, is the idea of optimizing shape and form for robots. So a lot of evolutionary and behavioral theory, drawing from psychology, tells us that brains and bodies that aren't well adapted, or forms that aren't specialized to a certain environmental niche, have to do a lot of thinking to solve tasks, where well-designed animal bodies or well-designed robots can solve those tasks really, really simply. And so we're going to try and look at the extremes of this, the extreme in engineering maybe being a passive walker, which walks down this inclined plane without any motors or control, just through clever design, adaptively using gravity to walk in this really fluid, lifelike motion. A place where this sort of embodiment and what we might call morphological computation, the inherent benefits of the structure and form of a robot are really important, is in soft robotics, where rather than doing kind of really complex dexterous manipulation of things, we had this really awesome project in our lab looking at soft robots that were just made out of a balloon with coffee grounds inside it. And so you can stick that balloon on any structure and it'll deform exactly around it, not using complex control, but just using normal forces from the rich interactions with its environment. And then it has just a single control degree of freedom, which is that this is hooked up to a shop vac. And when you turn the vacuum on, the coffee grounds inside of it jam against each other in the vacuum and lock into place, grabbing whatever structure the soft balloon is wrapped around as it becomes rigid. So this type of adaptability and smoothness and robustness and morphological computation, I think, is really at odds with kind of the current state of robotics, at least at the time. And especially when we look at the blooper reel of some of the best and brightest teams building robots, that these things work really well in ideal scenarios, but just like the robots in our manufacturing line, are really brittle and fragile when the slightest things go wrong. So we're going to try and combine the last 2 ideas of soft robots and design automation to try and automate the design of functional robots. Again, using kind of the minimal cognition necessary here. We're just going to have our palette be a whole bunch of these soft Jello cubes, of which a couple I've synced up out of phase on an oscillator. So again, really no high-level control or function. We're just looking at how we can optimize shape and form, as we might do if we were trying to 3D print some robots. sorry that this is over a Zoom call and the video is probably choppy here, but at least on my side, there's really smooth, really biological looking and feeling behaviors that fall out of no engineering feat of my own, just hooking this up to the evolutionary process of asking the system to find a configuration of cells that moves across the screen as quickly as possible. And each of these behaviors are so different and so effective. And just like we were able to look at how the beam in our first example grew and pruned itself like a tree growing towards the sun or trying to be robust to the wind, we see the evolutionary process here also holding on to certain aspects of functional behavior, carving out the middle here to make front and back limbs, finding that you can put two muscle groups opposing each other to articulate limbs back and forth, finding out that left-right symmetry is really helpful for making robots move in straight lines, and being able to fine-tune that behavior into something that's really effective and complex and lifelike. And I think that the kind of main lesson I take away from this is just the power of design automation. That, again, I'm a terrible engineer, but I don't think anyone would design a walking robot that doesn't have legs and flails its arms around like this one does. And yet it's an effective way, at least within the physical world that we live in here, of solving this problem. And this sort of divergent search and computational creativity, I think, is a really interesting phenomenon within this sort of evolutionary design automation for shape and form. Again, I could go on forever and ever about the different things that we've tried to get these robots to do, tying together form and function. This one I'll just flash quickly because I think it's really interesting for us to play God a little bit and take robots that are evolved underwater and bring them up on land, or vice versa, looking at early origins of life. But you looked at more practical engineering solutions, like having them squeeze through tight openings, or traverse different environments. We've tried to manufacture these in a whole bunch of different ways, looking at everything from electrically active polymers to big foam cubes that are mechanically driven. By far the best and most interesting version of this that I've come across is a couple of our collaborators here, as well as at Tufts, took the soft robot platform, and instead of trying to engineer mechanical robots, used it to design the shape and form of assemblies of living cells in what I still think is an absolutely wild and crazy sci-fi future. We're able to take frog cells, amalgamate them together, and do this microsurgery to carve out the shapes that we found with the design automation tools you just saw, to create functional, real living robots. And this is absolutely crazy to me, and we're working on building out the manufacturing infrastructure to make this process of designing and building these more automated and more scalable. The last thing I'll say about optimizing these robots is that there's, again, a whole nother talk I wish I could give about trying to add in complex control on top of this form and structure. And this is kind of even beyond what we've talked about in the proposal around the Northeast Integrated Manufacturing Lab, where we're trying to tie together brain and body of these systems. And it turns out that seems like it would be an easy thing to do if these things are so effective by themselves. If you add complex control on top of that, it should work even better. But it turns out that optimizing the brain and the body together becomes much more of a struggle, because we have a co-optimization process where the body depends on what the brain does and the brain depends on what the body does, and you get this fragile co-adaptation. That is, again, kind of this multi-layer, multimodal optimization, a little bit like I alluded to in the macro and micro structures within our bracket, but to an even greater extreme here. And I don't have time to get into the details, but we've found ways to get around the tight co-optimization and fragility that comes with that sort of specialization of brain and body, so that we're able to find forms that don't just find kind of immediate neighbors that are pretty good. You see on this plot on the left that after the first couple columns, the forms stagnate and converge to local optima. And using some tricks that we have in a kind of tool set of them that we're still actively developing, are able to find structures that can do a more global search and find what turn out to be far more optimal solutions within this search landscape, starting from the same exact point. And I think you can really see the premature convergence when you look at how early on within the scope of search these solutions are found in traditional approaches, where each of the different colors here is a different body plan and structure, that both the structures emerge very early, and we're not able to find good controllers that really are able to adapt and exploit these forms. But adding in our set of tricks, we're able to co-optimize brain and body in a way where we get continual innovation and evolutionary pressure to explore new areas of search and get around this fragile co-optimization of brain and body. There's a whole line of work there thinking about how you optimize structure for something that's actually going to be controlled in deployment. But I think instead of going into that aspect of robotics, I'll switch over and spend the last half of the talk focusing on the sort of robotics work that we're planning to do over the next 4 years as part of this project. So like I talked about, the robot arms in the manufacturing plant doing the same repetitive task over and over again. This is, of course, not like the way that we interact with the world. And this is also representative of the way that machine learning problems work in general. And I'm going to use computer vision, where a lot of our prior work has happened, as an analogy for this. And it's obviously related to the pick and place example that I opened the talk with. But I think is representative in a place where we're going to do a lot of experimentation before we hopefully move into robotics in the second half of this project. So the kind of big data approach, which is the way most machine learning models work now, is to assume that you have all the data you're ever going to see, that you've experienced everything in your lifetime, and then to be able to take all of that, randomly shuffle it up, put it in a blender, and feed it to your model all at once to try and get good at everything. And then to test on that same exact distribution of data. But that's not the way that creatures and animals and humans see the world. It's in a continual stream of highly correlated data that's coming at you sequentially. And you have to be able to move from one task to focusing on another one, and not forget about what you've seen before, but leverage the knowledge that you've gained in exploiting new opportunities. And just like we learn to do some task like ride a bike, if my kids do this and then later recycle some of those same skills to learn how to drive a car or ride a lawnmower, we can borrow the aspects of each of those tasks, which are similar, to try and leverage the same sort of motor primitives. But we can also do this for tasks that are transferring to slightly more afar or maybe more abstractly related things, like going from riding a bike to understanding how a bike works so that you might be able to help fix your dad's bike. This idea in machine learning works extremely well in cases where we have a big data set to transfer from. This idea we typically call transfer learning, where we train a big neural network to grab a bunch of features that are important to the task that we want to do, kind of the traditional machine learning approach, and then we take those features and learn actions for a robot or decisions for a classifier to solve some given problem. And then we can transfer those same features and assume that they're also good for some secondary task, which we have far less data for. And we don't have to learn those features, but can just learn how to use those to make actions and decisions in another context. This assumes that you have a bunch of really high quality data you could train on ahead of time, and assumes that everything that you will transfer to is highly related to where you've come from. So this really only works in certain scenarios, and really only for a couple of tasks, typically just transferring from one task to a second. But the process that we undergo as learning agents in biology is much more like these long sequences where we see one in task or environment, we go to a different context and have to do something totally different. We see a new set of stimuli later in time, and what we're optimized for, what we're evaluated on, is really not how we do on any one of those things, but how good we are at the next thing, how adaptable we are to future unknown scenarios. And this is a paradigm that we think of as few-shot learning, and this is the case where I'm going to focus on for the next handful of examples. So this few-shot learning task, there's actually a really nice tool set for if we assume we know the distribution of tasks beforehand. We can find a good starting spot that is relatively close in state space to all of the places where we might want to adapt to. Robots that are close to being able to do all the things that we might expect our robot to need to do in whatever complex manufacturing multitask cell or scenario it's working within. And can use some fancy approaches like meta-learning to try and find the optimal starting point that most rapidly adapts to all of these tasks. But actually, the scenario described of online continual learning doesn't necessarily assume you know even the distribution of tasks ahead of time, and you really are just kind of seeing them one-off as you go through life and experience this stream of new things coming at you. And you kind of never see the whole set. You never see the whole set kind of before you start. So the analogy we're going to use here is just a classification task on the popular data set ImageNet. We'll have some examples from handwritten digits in Omniglot as well. Well, let's say we're training on some long sequences where we show a bunch of examples of a single class, like a dog, and then a bunch of examples of a zebra and a bunch of examples of apples. And we train on these sequential trajectories. When we go to evaluate our system, we're not necessarily going to care about how well we do on those training sets, but are going to give a whole brand new sequence of a bunch of things and are going to ask how well we can distinguish an orange or a boat from the type of features we learned to help classify, dogs versus cars. So we're asking about sequential correlated trajectories, really hard for traditional machine learning, on classes that it's never seen during training time. It's out of distribution generalization, which we call, is also really hard for traditional machine learning. And it comes with a especially kind of malicious failure mode, which is that deep neural networks are extremely efficient because they're able to adapt all of their parameters at once to try and better map inputs to outputs, to classification labels or rewards and reinforcement learning. And that's great for quickly and efficiently learning some task when you have millions of parameters in your network. But that same mechanism, when you go from one task to focusing solely on a second task within one of these long continual learning sequences, means that all of your parameters now adapt really rapidly to the new thing that you're looking at and overwrite essentially all of the knowledge of decision-making that you had in your prior task. And of course, humans aren't like that. We remember old things, just like riding a bike. So a bunch of us from the machine learning and robotics side of things teamed up with a bunch of really awesome biologists to try and think about opportunities for biologically inspired continual lifelong learning machines. And looked at what sort of things might be important for these streams of new tasks in some open-ended autonomous, for example, manufacturing system. We came up with a whole list of important things, some of which I've talked about already, of transfer learning and catastrophic forgetting, and also came up with a bunch of biologically inspired mechanisms which might be relevant and helpful for solving these tasks. In the next couple papers, I'm going to talk about a few of these that we've especially explored within my lab, looking at things like neurogenesis, neuromodulation, metaplasticity, and show examples of how we can design deep neural networks that might include these sort of features and be better at adapting to new unforeseen circumstances like we want our robots to be able to do. So we're building off of, like I talked about before, this meta-learning idea of trying to find good starting points for rapidly adapting to a bunch of tasks. And we're going to do that in what is analogous to the transfer learning scenario we talked about before, where we're going to use meta-learning now to find a bunch of really good generalizable features. And then we're going to build classifiers on each of our individual tasks, or kind of mini data sets, data streams, within the meta-learning process. We took a slightly different approach to this, and said instead, one of the ways we're going to try and prevent catastrophic forgetting and overwriting is adding in metaplasticity and neuromodulation, where we have this system that's not only able to learn what it should be doing, but is able to take its context, in this case, the image stimuli it's being shown, but in a robot, kind of a much more complex context, and decide which parts of the network it should use for any given input. We had ideas that this would let us kind of find specific quote unquote brain regions within these networks that would differently react to certain tasks, and we kind of get this really clean modularity within the network. I won't go too far into that intuition there, because it turned out that wasn't really what happened, and neuromodulation wasn't working the way that we thought it was. But the results, I think, speak for themselves, where if you're looking at how well we do on these long test sequences, traditional deep learning, as you might have guessed from how I set things up, immediately fails and catastrophically overwrites everything it's seen for a sequence of virtually any length. If we do traditional transfer learning, we start at a better point. We have more generalizable, higher quality features to start with, but overwriting and catastrophic forgetting eventually totally wreck any performance that was in this network to begin with. The meta-learned feature forget over time, but are able to have some non-zero performance at the end of this sequence. We were able to take the previous meta-learning approach and tune some of the hyperparameters to make it so that it adapted a bit more slowly, but overrode itself much less, to have much better performance at the end of these sequences. But I wouldn't be showing you this plot if our neuroplasticity approach wasn't much better at both quickly as well as maintaining features through much longer sequences. To think about what the upper bound on each of these models are, we treated them not just in the sequential case of looking at one scenario and then the other in these long sequences of lifelong learning, but also showed the randomly shuffled data case, where our imagined robot kind of knows all the things it might have to do ahead of time. And when we compare those two, we can see kind of just how much of our performance is lost when we move to the continual learning case. With our neuromodulated meta-learning approach, we see that we've closed the gap, and our continual learner is actually very close to the ceiling it would be in the traditional deep learning IID, identical and independent and identically distributed data setting, where the other approaches see this catastrophic failure when we go from the traditional shuffled data into these continual learning frameworks. So whether or not neuromodulation is working the way we thought it would, we've kind of made a lot of progress on these sequential learning tasks. And that's even more obvious when you look at not generalization performance to kind of brand new, never before seen validation sets, which is the gold standard in machine learning. But if we look at just memorization of our training data, our approach almost perfectly remembers everything it's seen during during these sequences of brand new tasks, which it hasn't learned features for before, where the other approaches fall off much more. What really clued us into something odd happening, though, is when we took this shuffled traditional learning approach, and instead of doing the kind of one sequence through, which we had in the continual learning case, and what our plots I just showed on the last case was a shuffled version of seeing each data point once, and turned into a much more traditional machine learning case where you're seeing each data point shuffled many, many times and doing iterative updates to your model. And weirdly, our model was still performing better, even though there wasn't kind of any forgetting any continual learning happening in this case. And that seemed really strange because we had designed the process kind of especially around the idea of minimizing catastrophic forgetting and overwriting with our neural plasticity. So we did a bunch of ablation studies to try and figure out what's actually driving behavior in this case, and came up with, I think, a really interesting hypothesis that's in review now, where we, one of the tricks that we used during training was to reset the weights going into the class that we were about to learn. We did this just for kind of computational reasons to try and make the gradients during training behave a little bit more cleanly. And yet it seems like what that actually did was to treat each training sequence during our meta learning process as a mini transfer learning task of using the features, but then resetting the classifier that was about to do that task. And so in that way, we've kind of practiced doing transfer learning hundreds or thousands of times within our training sequence and become really good at it for both continual learning and transfer learning in a more traditional approach with these networks that we've created. You see that here. We call this resetting zapping very affectionately, and you see the dotted lines for the zapped networks are outperforming the non-zapped approaches in this transfer learning task. We see this in lots of settings, the meta-learning setting, a sequential setting without meta-learning, but even in the IID setting, the traditional shuffled data approach, which we didn't expect at all. And the differences are even more extreme when we look at continual learning cases for this same approach. The simple zapping is really effective in both, and I think gives us just really good, really transferable features. There's a lot more future work that we hope to do to understand the mechanism and cause a little bit more here, but the empirical results are at least really promising, at least in this early stage. And so that actually turned out to be much more of a driver of the results you just saw in our neuromodulated meta-learning platform than the neuroplasticity, which we thought would be the main crucial ingredient here. But this neuroplasticity wasn't all for naught. When we gave our network an even harder scenario where we weren't transferring from some types of images and pictures to other types of photographs, but made it a much harder out-of-domain transfer, learning a network to do handwritten digit characterization and then trying to transfer it to real-life high-res photographs. This should really work. We set this up as a control case of the hardest thing it could possibly throw at our networks. And it took a lot of toying around. My PhD student Sean spent a lot of time trying to figure out configurations that worked. And it turns out that the most effective one was one that highly leveraged neuroplasticity, not for creating modules the way that we thought it would, but for actually kind of regulating the size of the network. So if we started that was mostly turned off and let meta learning adapt how sensitive these neurons were to different stimuli, we saw this rapid growth and then this really smooth decay of how active the network was for any given stimuli, which at least me, trying to find connections to biology for everything. I got really excited that this felt a lot to me like rapid neurogenesis early in life and then synaptic pruning throughout learning and into adolescence. Empirically, this tends to work a lot better than the traditional approach of initializing with dense neural networks and then trying to kind of sculpt out a subnetwork within that. Again, we're still trying to figure out the mechanism of why this works, but the empirical results show that on this super complex transfer task of learning on handwritten characters and then trying to use those features in photographs, our starting small and growing approach really shines in our setup, but especially in a data sparse setup where we give the network not very much training data to meta learn on. And so we think that this mechanism of starting small and growing is especially helpful when we have not much data, which as we move into a robotic context where we're actually going to have to do real life demonstrations, or at the very least fairly expensive simulations, being able to find models that work in a data scarce region, I think will be especially helpful and important. There's lots of really interesting properties about how these mechanisms choose to turn on and off over time for different stimuli that I think I'll skip for the sake of time here. To get to one more example, which is again thinking about how we can do few-shot learning in a really efficient way. So the surprising result here is that in machine learning, we typically have the rule that the best thing you can do is try and train on data that's as similarly distributed to the data that you ultimately want to test on, within distribution generalization. We found an example where we can train on a slightly different data set and actually get better results. There's some findings in transfer learning that suggest that this is the case, but ours is specific to few-shot learning. And at least the rationale that we're working on as our initial hypothesis is a very kind of few-shot learning motivated approach. So here we have an example of a class from ImageNet. In this case, it's mailboxes, and taking a random sample of 20 mailboxes, you see lots of diversity within them. And usually we think of this diversity within training as being really good and really helpful because it helps you find what's the boundary of a mailbox. And you can have the ones that look like R2-D2 or that are covered in snow, and yet they're still mailboxes. It helps you form a better, more complete understanding of what this concept is. We took the exact opposite approach and instead trained it on the 20 most self-similar examples of mailboxes within this data set. And we're losing a lot of the variation of understanding what a mailbox is. But again, remember, in our continual learning case, we don't care about transferring to some model that's really good at mailboxes because we're looking at transferring to brand new classes and brand new domains. And so the boundaries of what's a mailbox and not doesn't really matter when you're looking at telling apart oranges versus boats. But having really simple, concise classes where you can train a model to most efficiently tell a mailbox from bubbles or a hot air balloon or an Arctic wolf turns out in few shots to find classifiers that are much more effective and create much more useful and generalizable features that transfer to brand new unseen tasks before. And so that's how we get better few-shot generalization, looking at data sets with more consistency than more variation. Again, this doesn't really matter that much here for ImageNet because we already have all the labeled data. Why don't you just use all 1,000 classes instead of pretending it's a few-shot learning domain? But in real life scenarios, we might be dealing with active data collection and energy and time and cost constraints there and trying to figure out if we're collecting data, what sort of data is most useful for few-shot learning? Seems like a really important question to ask. I'm nearing time, so I'll wrap up, but I just want to say there are so many other questions that I haven't had time to talk about, like what are the best neural network structures for generalization, transfer, continual learning? How can we leverage transferring not just tasks from features from one task to another, but actually leveraging totally untrained networks. There's really interesting data and compute efficient solutions that use totally random networks that I think tell us actually a lot about how fundamental machine learning works in these deep neural networks that also is really time and data efficient. But to pull things back out to wrap up, I hope that I've convinced you that there are interesting opportunities for AI in manufacturing when we think about Industry 4.0, and that we can start to think about tools for design automation or ways in which we can adapt to brand new stimuli in uncontrolled, non-pristine environments that manufacturing floors may look more like as we start to get to more adaptable, more robust, and more customizable pipelines, rather than these really rigid assembly lines. And I think that there's both really fundamental work on bio-inspired design for neural networks and machine learning, but I also think that there's really helpful, well fleshed out opportunities for us to collaborate with the set of really fantastic engineers and industry partners that we have within this collaboration. And so I'm really excited about diving deeper into this on both sides of this over the next 4 years. I'll end just by pitching one more area of possible collaboration that can happen right now, which is that here at UVM, at least, we have a bunch of project-based machine learning, AI, data science, deep learning courses taught by some of the faculty on this grant, but also a bunch of us throughout the university. And we're looking for real life data and questions that you think are good for a data scientist in training to bite off in a 6-week project, that maybe aren't critical path things for you, since we might not get to them for a semester or two, but are opportunities where you'd like to collaborate with some of the data science capacity that we have here, and where we can start to get students experience and networking working on real life problems. So if any of that sounds interesting or you want to learn more about it, please email us at data@uvm.edu or reach out to me after the talk. A huge thanks to a bunch of awesome people who've helped with this work, and even some work here that I haven't had time to talk about in just an hour. And I have a few minutes for questions, but I'm also happy to continue the conversation afterwards if we run out of time, or for those watching this asynchronously. So here's my email, and please reach out and we can chat. Thanks.